Hello, welcome back. The title of this lesson is called Periodic Functions and Even and Odd Functions Part 1. This is actually a really important lesson because I can't get too much into the weeds right now, but everything we learn in this lesson is actually applicable to a great many topics in the future when you get into higher level math and also into engineering. So here we're going to talk about the concept of a periodic function. I'll give you a little bit of the punchline because where we're going is we're going to first talk about periodic functions and what they are. And those are functions that just repeat themselves over and over again. You might say, why do we care about that? Well, the most famous and useful periodic functions that we're going to examine in this lesson and over the next few lessons is the graphs of the sine and the cosine function. So you already know what the sine of an angle is, you know what the cosine of an angle is, and we use the unit circle, and you know how to do all that already. In this lesson, we're going to introduce the idea of graphing those functions to get a picture of what the thing looks like. And what we're going to find is that the sine and the cosine function, they look like waves. And they're repeating waves. They repeat over and over and over again. And you're going to understand why soon enough, but I'll give you the punchline. The reason the sine and the cosine repeat themselves is because the unit circle is a circle. And as you go around it over and over and over and over and over again, you keep getting the same values for the sine and the cosine because a circle just repeats itself. And that's the reason why the sine and the cosine repeat itself. But fundamentally, where we're going with this, once we learn how to graph sine and cosine, is we're going to learn how to graph the other trig functions. But I want you to know in the back of your mind, the reason why we care about this is a lot of reasons. It's because most of the modern theories of physics and a lot of theories in math are what we call wave theories. And what I mean by that is the entire concept and the study of quantum mechanics, which this is not a class on quantum mechanics, but I'm trying to motivate you. The entire idea of quantum mechanics is based upon a wave theory. All matter and energy really are modeled as waves. And what kind of waves? Sine and cosine waves. All right, now it's a little more complicated than that. I'm boiling it down a little bit, probably more than I should. But still, the sines and cosines pop up in quantum mechanics all the time. And when things travel, like energy in a photon of light coming from the sun, we model it as a sine or a cosine wave. So you can see how important knowing how to graph sines and cosines, knowing what a periodic function is, when you know that all of the modern theories of basically physics are all based upon waves. So we have to start here. Now, we don't want to go too fast, but we also don't want to go too slow. So here we're going to talk about periodic functions and the concept of an even and an odd function. And later on, we're going to be graphing more and more of these. And then we're going to have entire lessons on graphing sine and cosine. So we're just introducing it here. We're not getting into every little detail. We have to break it up over many lessons. Now that is a big introduction, but it's important because a lot of students look at this and they're like, why do I care about this? Well, you care about it because most modern theories of science are based on waves, sine and cosine waves, essentially. So what is a periodic function? So you all know what a function is. A function is when we have an input that goes into a calculation, we call it f of x, and then a value comes out as the output. And we can graph those. We can make little XY graphs. Now, we used to call them XY graphs. Now we call them X graphed versus f of x. F of x is the output of the function. So a function is essentially periodic if the function repeats itself. If you think about a wave going up and down and up and down and up and down, and it just goes on forever like that, and it always repeats, that's called periodic. But a lot of functions in real life or in situations are actually not periodic functions. So let me show you a couple of quick examples of that. So let's say that I'm going to graph a function that is not periodic. So you could say this is the x axis and this is the f of x axis. So we used to call it y, now we call it f of x because it's a function of the input, which is called x. So what would be an example of a non-periodic function? Well, that would be a function that would look like this. It goes up, down, up like this, something like that. You see? It may look like there's some periodic nature of the wiggles, but really they're not. You cannot identify where this thing starts over exactly. I mean, yes, this looks a little bit like this, but I don't see any of this repeated anywhere else, and so it's not periodic. So we can say that this is not periodic. What would be an example of a function in real life that's not periodic? Well, if you have a microphone hooked up to an amplifier, and you're listening to the static, that's basically just the vibrations of the microphone because of the air currents or something, you know, that little whatever, that's not a periodic function. It's a random noise kind of situation. right? So it's not going to have a periodic shape. It's just going to be random up and down. Maybe the stock market. If you actually look at a plot of the stock market, you don't see a periodic nature. You see some ups, some downs, some ups, some downs, maybe a little bit more up, a little bit more down, but it never just nice and repeats itself. All right, so let's take a look at an example of a periodic function. Now, as I go through talking about all this stuff, I'm going to draw sines and cosines a lot. I could draw lots of different periodic functions to illustrate the point here, but I'm subconsciously trying to influence you to get used to seeing waves. Now, we haven't learned why sine and cosine have the shape of a wave. That comes later. I'll show you exactly why when you plot a sine function, it generates this nice wave. I can't do everything at once. So for now, just take my word for it that when you plot a sine function, it graphs a nice little wave, right? And a cosine function also generates a nice little wave as well. So what would something like that look like? It would look like something like this. Now, I'm not perfect artist, but it would go up and then down and then up like this. And then if you continue this way, it would be down and then up and then down. Now, I'm not a perfect artist, so my graph is not exactly right. Like this exact height is not exactly the same height as this one. This trough is not exactly the same, and the shape of them are not exactly the same. So you have to remember that I'm not a computer. So this is supposed to be an exact carbon copy of this. But you see the difference between these two. This is called periodic function. Right? And the reason is just so obvious, right? It's because it's, you know, if you pick any point on this graph, let's say here, you go down and then up, it starts over. Then down and then up, it starts over. If you pick a different point on the function, let's pick this trough. Up and then down, starts over. Up and then down, starts over. You see how it starts over. Now you can have many different shapes of periodic functions. Here I drew, this is what we're going to learn later, is a sine function or a sine wave. All right, but there's cosine. You know, lots of functions are periodic, right? You could even have triangles where the triangle goes up and then down and up and then down. It doesn't have to be smooth like this. But the sine and the cosine are so important that I'm going to draw them a lot because I want you to be very intimately familiar with that. Now, if we have a periodic function like this one, then we can say that it repeats over some interval. And the interval over which it repeats is called the period of the function. So when I tell you, here's a function, and the period is whatever, 5, then that is the distance along the x-axis that the thing it starts to repeat. So for instance, I can say, where would be the best place to put like here? You see how it's going up through the x-axis, and then it's going down, and then it's going back up through the x-axis. So I could say this distance right here, this is called the period P. That's the period P, right? Now, the period is a number. So you see I've got the x-axis here, but you might also consider that these could be waves that are waving up and down in time. So right now I've got it as x for the horizontal and f of x for the vertical, and that's like if I had a string stretched out in space. Then if the period were, if this were meters, if x were in meters and f of x were in meters, and if the period over here, if I literally have it stretched out in front of me so that it starts to repeat after like 2 meters, then the period would be 2 meters, right? But if this is a wave in time where it's just going up and down, over some period of time, it repeats itself. Maybe after 6 seconds, it repeats itself. Then the period would be 6 seconds. Sometimes you have waves in space where they're stretched out in space. Sometimes you have waves in time where it's just oscillating up and down over some period of time. So the period can be expressed depending on what kind of wave you have. In this case, I'm just drawing a generic graph. We graph it. We say the period is this many distance units, whatever it is I'm talking about here. So let me give you an example of how we would use this. Let me give you what we call a snippet of a periodic function, and we're going to draw the full periodic function. All right, what I'm going to do now is I'm going to give you a fragment of a function. All right, so let me give you a fragment of this function. I'm going to draw it right here, and this is the x, and this is the f of x. Now I could draw a fragment of a sine wave, but let's do something different just so we're not drawing the same things over and over and over again. All right, let's say this is 1, and right here is also 1, and right here is also 1, like this. And just to see if I can do it right, let me put a dot there, put a dot there, I'll put a dot there. Now I'm drawing it freehand, okay? So you're gonna have to forgive me. So I'm gonna try to draw a straight line from here down to here, and I'll draw a straight line from here. Actually, I want it to be more like down here, so I erased that little dot down here. So this is a snippet. So I've graphed a function from -1 over to, whoops, this should be -1, sorry about that, -1 over to +1, and it goes up to a value of +1, and this, you could say this is value of -1 down here, like this, and this is a snippet of a larger function. So if this function has a period equal to 2, graph it. I'm trying to get you to understand the idea of what a periodic function is. So the period of a function is the horizontal distance over which the thing is starting to repeat itself. If I tell you that a function is periodic, then it literally goes on forever in both directions, negative and positive directions, and it continues to repeat forever and ever and ever and ever and ever, and it never stops repeating. And I'm going to tell you that this is a fragment or a snippet of a function. If this function has a period equal to 2, I want to graph it. So let's go ahead and draw a larger xy axis down here, and I'll make it much, much bigger. So this is x, this is f of x. Now, if this thing has a period of 2, that means that just like we had here, it repeats itself after that many distance units. So you can see the snippet I drew you, the distance between here and here is 2. This is a distance of 1, and this is a distance of another 1. So together, the width of this whole thing is a width of 2. So what it's saying is when I draw this function down here, I should be able to look at widths that are 2 units wide, and the thing is going to keep repeating itself over and over again. So what would this thing look like here? Well, let's mark this as 1. Let's mark this as -1. And we'll try to kind of carry this down. This is 1 right here. And down here, right here, this is -1 right here. And so if this is 1, over here we'll put this as 2. And over here we'll put this as 3. And then over here we'll put this as -2. And over here we'll put -3, like this. All right, so what would this look like? Well, we already know that it goes here, up to here, and it goes down here. So I'll try to do my best to draw it. It's not going to be perfect, so please forgive me, but that's basically this. And then this is going to try to go down to here, like this. Okay, now what's going to happen? The thing is going to repeat itself again. So it's going to go up over here, it's going to reach a maximum right here, and then it's go down over here. And so what we're going to have is this is going to go like this, and then it's going to go down like this. And then over here, we're going to have a maximum right here, and then we're going to have another minimum over here. So this one's going to go like this, and this one is going to go down like this. Now, does this make sense? If this function has a period of 2, graph it. So if I just gave you this function and said, is this function periodic? Would you say yes or no? Yes, it's periodic. You can clearly see it's repeating itself over and over again. That's all you need to know if it's periodic. What is the period of this function? Well, you just have to identify any 2 same points and see what the period is, the distance there. So if I pick peak to peak, the next peak over, what is the distance here? Well, this is 2 distance units, so the period is 2. If I pick this peak and this peak, what is the width here? The distance is 2 distance units, period is still 2. What if I pick the 2 troughs here? The distance is still 2. What if I pick these 2 troughs? The distance is still 2. What if I pick these 2 troughs? The distance is still 2. So you pick any 2 points on the graph where you believe it's starting to repeat itself. You see, from here to here, I believe it's starting to repeat itself again. From here to here, it's repeating itself again. From here to here, again, repeating itself. So on a periodic function, no matter what 2 points you pick on the function where you believe it's repeating itself, the period will be the same because it's periodic. It's repeating the same shape over and over again. So I give you a snippet, give you the period, you should be able to reproduce what the graph looks like. This is a periodic function. Now, the beginning of this lesson here with periodic functions, pretty easy, I think, for most people to understand because it's pretty obvious to see the thing repeating itself. Now we have to put our big boys and girls clothes on, okay? We have to grow up a little bit because the next part of the lesson is a little bit more involved, but I do believe that I can break it down in such a way that it's very easy to understand. But you are going to have to follow me all the way to the end. And here's where we get into a little bit more detail with sine and cosine. And it's a little tricky because we haven't graphed these functions yet. And I have an entire lesson coming up where we actually graph them and go into great detail. But I also have to show you the graph here as well. So before we go any farther, let me just reveal and show you the graph of the sine and the cosine function. Now I'm going to draw these by hand a lot, but I do want to have some pretty graphs, some perfect graphs, so you can see what they really look like. So this is a graph of a sine function. All right, and here, down here is the graph of the cosine function. The first thing I want you to do is notice that the shape of the sine function graph is exactly the shape of the cosine function graph. The only real difference is that between these two, the sine and the cosine curves are shifted relative to each other. So we're going to get into why later. You might have to hold a little bit of your questions because you want to ask immediately, well, why are they the same shape? Well, I have to do one thing before I do another thing. So I promise I will answer that question. But if you were to grab this thing, notice the peak is right here. If I could graph the thing and just pull it this way so that the peak goes here, then what you would get would be the cosine. The peak starts at the top and then it goes down and then again it repeats and so on. So these are exactly the same shape. All right. And I'll give you a little bit of the punchline. The reason they're the same shape is because when we look at the unit circle, the sine and the cosine are the projections on the unit circle as we sweep around. So we'll get there when I draw a unit circle, but those projections are the same for sine and cosine, but they're just shifted relative to each other because the sine is projected on the y-axis and the cosine is projected on the x-axis. The projections end up looking the same, but at different points on the circle, they're just shifted relative to one another. That's the reason why these are the same graph, just shifted relative to one another. Now, first of all, are these periodic functions? Obviously they are. This thing repeats, and then it repeats again. And over here, if I start here, it repeats, and then it repeats again. If I pick a different point, trough, then I could say it repeats down here. And then it would repeat off the graph over there. Now, what do you think the period of this function would be? All you have to do is pick any 2 points on the graph where the thing starts to repeat itself, and that is the period. So you could pick literally these points here. You could pick these points here because you can see that it's starting to repeat itself here. But I'm going to pick this because it's going to be a little easier. Notice it goes up and then down and then back up again, and it's going to start over. So if I look between here, and then over here, what is the period? All you got to do to figure out the period is take a look from here to here, what is the width? And the width is, here's pi over 2, this is in radians, this is pi radians, this is 3 pi over 2 radians, and this is 2 pi radians. So the distance over which in the x-axis the thing repeats is 2 pi. Now, I want to stop for a second and say that all of your graphing up until this point, on the x-axis, they're just numbers. You know, when we graph functions, like just regular functions, like f of x equals x squared, then on the x-axis you have numbers, and on the y-axis you have, or the f of x-axis, you have more numbers. 1, 2, 3, 4, 1, 2, 3, 4. But in the trig world, where we're graphing sines and cosines and tangents, we very often replace the numbers on the x-axis here. Instead of just 1, 2, 3, 4, we replace them with multiples of pi. And the reason is because if you remember back, again, I'm going to get into this very detailed in the subsequent lessons. But the way we come up with these functions is we look in the unit circle and we look at different angles. And if you remember, for instance, at, let's just say pi over 2 radians, that's when the unit circle, when you're looking straight up and down at pi over 2 radians, what is the sine of pi over 2? The sine of pi over 2 is 1. So right here at pi over 2, the answer that you get for the sine is 1. Because if you can visualize a unit circle, then pi over 2 radians is straight up and down, and the sine function is the projection on the y-axis, so the sine of pi over 2 is 1. That's why it's 1 up here. But what would be the cosine of that projection? Well, the cosine is the projection on the x-axis. So if you were up and down at 90 degrees, pi over 2, the projection on the x-axis is 0, so the cosine of pi over 2 is 0. That's why for the cosine function, it crosses through the 0 point there at pi over 2 radians. And as you go around the unit circle, then the y projection is getting bigger and smaller, and the x projection is also getting bigger and smaller, and it traces out these functions here. But these numbers along the x-axis, it makes a lot more sense to put them in terms of pi, because for sine and cosine, the special numbers, the easy numbers on the unit circle are pi over 2 radians, pi radians over here, and then 3 pi over 2, and then back to 2 pi. 2 pi radians would go all the way around the circle one whole time, right? That's why it repeats itself after 2 pi radians, because we have come back to our starting point. We have come back to our starting point after 2 pi radians. So when you see pi's running along the x-axis, don't flip out. Remember, pi is a number, 3.14159 and an infinite number of decimals. So here when I have pi here, this just means instead of 1, 2, 3, 4 or whatever along the x-axis, this is 3.14159 is the number along the x-axis. This is that number divided by 2. This is 2 times that number pi. So don't get so scared when you see pi's on the x-axis. It's just that those are the special numbers that are applicable to trig functions. That's why we relabel them down there, okay? And I just pointed that out with pi over 2. You get the sine of 1. And the sine of pi is 0 on the unit circle, so it's another special number, and so on, all right? Now, what is the period of this function? We just said it starts to repeat from here, and it starts to repeat again, and that is a distance from here to here of 2 pi. That's why the period is 2 pi. There, 2 pi in terms of radians for the x variable. But what if I picked something different? Let's say I picked it from, let's say from here, and it goes up and then down and then up. It starts to repeat again. What is the distance from here to here? Well, this is negative 2 pi. This is 0. The distance between them is still 2 pi radians, so the period is 2 pi if I pick these two numbers. What happens if I pick these two numbers? It appears that it's going to repeat itself again. Well, what I'm going to have is the distance from here to here is pi over 2, and the distance this direction is negative 3 pi over 2, but the absolute value is 3 pi over 2. If you take the 3 pi over 2 and you add to it another pi over 2, you're going to get 4 pi over 2, and 4 pi over 2 is 2 pi, right? Let me just double check that. 4 pi over 2 is 2 pi. So the distance here is, again, 2 pi. So no matter what 2 points you pick on this graph, you're going to get exactly the same period as long as it's starting to repeat at that point. And the period of a sine function, an unadulterated, unchanged, unmodified sine function is 2 pi. Why? Because we go around the unit circle back to 2 pi, it starts to repeat itself because it's a circle, and the circle comes back and starts over at 2 pi radians. Now let's go back and look at the cosine. Where does this thing start to repeat? We can see it starts at a maximum for the cosine, and then it goes down, and then it comes back up to the same maximum. It looks like it repeats right here. So right here, I could say, from here to here is where one period is, and the period is what? This is 0, and this is 2 pi. 2 pi. So what we've learned is that the period of the sine function is 2 pi radians. And the period of a cosine function is also 2 pi radians. And so they have the same period. And we've learned that the shape of the sine function is exactly the same as the shape of a cosine function. They're just shifted. Because remember, if I grab this thing and pull this entire graph to the left so that the maximum is here, then I get exactly the cosine function. I'm pointing this out to you because it's actually really important as we get higher level math. Sine functions and cosine functions can be written in terms of each other because they really are the same function. It's just that one is shifted relative to the other. They're the same shape, they have the same maximum and minimum, they have the same period, which means we'll talk about frequency later, they have the same frequency, and they come from the same unit circle. So that's why they're basically the same shape, but they are shifted with respect to one another. So just a little bit of an aside, some books, when you write down wave equations and talk about how waves propagate, they write them down in terms of sine functions. Usually in physics, you'll see it written in terms of a sine function. But in engineering, a lot of times when we write down the wave equation of a traveling wave, we write it down in terms of cosines. Which one is correct? Well, they're the same thing. They're the same shape. They're the same period. They're the same everything. It's just one is shifted. So you can write down a wave equation, the description of a wave, in terms of sines or cosines, and it's really mathematically the same. But you do have to shift one. They have to be shifted to be the same, but they are the same shape. So sines and cosines, not so different. They're very close cousins of one another. So at this point, you should understand, even though we don't know exactly how the shape of the wave comes for sine and cosine, you should understand more or less what it is. What I want to do now is I want to kind of go through the same thing, talking about the period of a periodic function, and we need to talk about the idea of an even and an odd function. And I'm going to draw the unit circle. We're going to go through that and talk about the idea of an even and an odd function. Even and odd functions are very easy to understand, but the textbook definition of what they are is hard for most students to understand in the beginning. So I'm going to show you, and we're going to talk about it, but I promise if you just get to the end of it with me and kind of cut through what I'm telling you, then at the end it will be crystal clear, but please don't skip because it is important that we get there in the way in which I want to get you there. So I'm going to write a note here. Note. If I take the sine of some negative angle, and by the way, when I say negative angle, when I've graphed these things, I'm graphing them versus x. X is the input to the sine function. But you all know that the input to a sine is an angle in radians. So when you graph these things, sometimes you might see x and then sine of x, or you might see this labeled as theta, where theta is just another variable instead of x to represent that it's an angle, to remind you that it's an angle. And then it would be sine of theta. So if you see me write down sine of x, you need to remember that x is an angle in radians. Or if I write down sine of theta, theta is the angle in radians. The variable that you use to represent what's in here, it doesn't matter. The point is whatever goes in here is an angle in radians, and then whatever comes out is whatever comes out, okay? So what we're going to do here is I'm going to write down something that's not going to make any sense at first, but I'm going to explain it to you. The sine of, if I take negative, the negative of an angle, is equal to the negative sine of an angle. Now this is what you would see in a book, and this doesn't make any sense at first. Most people look at it and they're like, what does this mean? Most people actually just ignore it and say, well, I don't need to know that, so I'll just skip it. But stick with me, okay, I promise. All right, let's talk about why this is the case. And I guess we'll just go from there. So let's draw over here just a little unit circle to have something so that I can point to. So what I'm going to do is say, all right, here is a unit circle, which remember is a circle of radius 1. You could say this is x, you could say this is y, that kind of thing. All right, so for this guy, we're going to be talking about the sine, okay? So let's say that I'm up here at some angle theta, and remember theta is always relative to the x-axis here. So this is theta radians up, okay? How would I calculate the sine of this angle? All right, the sine of an angle is always the projection of that ray onto the y-axis. Remember, the sine goes with the y-axis, and the cosine of this ray is the projection onto the x-axis. That's exactly what it is. So if I wanted to figure out what the sine of this angle is, all I would do is literally draw a line over here, and I would basically say that this projection from here up to here is the sine of this angle right here, right? But notice that I'm going to get a positive number because these are all positive y values right here. Now, what I'm trying to say here is, let me draw a mirror image down below. What would this angle be down here? Well, if this is theta radians up, of course I could go all the way around here, but I could also express this as a negative angle. I could say that this angle right here is negative theta right here. And negative theta, what would be the sine of this negative theta angle? Well, it's the same thing. It's the projection onto the y-axis. So what I would do is I would project it right here. So notice what's going on here. If we look at the negative angle, which is just a mirror image of this one, down here, we're projecting for the sine of this guy. To find the sine of it, we're projecting here. And since these are negative numbers down here, we're going to get a negative answer. But the answer will be the same. If we take the sine of an angle, we're going to get a positive number. But if we take the sine of the negative of the same angle, we're going to get the same number, but it's going to be negative because it's down here. That's what this is trying to tell you. If I take the sine of a negative angle, which is this one, I'm going to get an answer, and it's going to be the negative of the sine of the positive version of the angle. Let me say that one more time. If I take the sine of a negative angle, that would be taking the sine of this. I'm going to get an answer, and it's going to be the negative of whatever the positive version of the angle returned, because this returned a positive there. So if I take the sine of a negative angle, I get an answer. It's going to be the negative of whatever the mirror image is, and that's because for the sine, when we take negative and positive mirror image angles, we get the same exact number but opposite signs like this. All right? Now let's take a look at that and just hold that in your mind. We just said that a few times. Hold that in your mind. Let's look at the graph of the sine function. Notice what's happening for the graph. If we take a look at the positive angle here, let's say pi over 2, we get a sine of 1, right? But if we go to the negative of the exact same angle, which means mirror image reflection, same as we were doing there, and we take the sine, we get exactly the same number, but it's negative of the positive version here. If we look at 3 pi over 2, we get a sine of negative 1. But if we go to the mirror image reflection, negative 3 pi over 2, we get exactly a negative answer of what we got over here. And that comes back to the definition of the sine and this. It's because if we look at the negative version of the same angle, we get the same exact number, but it's just the negative sign right here. Pick any number on here. Let's take a look at, well, I guess I've already looked at all the interesting ones here. But if you just pick this one, for instance, like even in between these two angles, this one right here, then in between these two angles here, between the negative pi over 2 and the pi, it's going to be down here. Notice that this is going to be exactly the same number as this one. It's just one's negative and one's positive. So that is called being an odd function. When you look at the mirror image reflection and you get the same number but they're just opposite signs like that, then it's like this graph is like, it's like a mirror image reflection across the origin. Notice how this is the mirror image of this. This would be the mirror image of this. So any positive angle that you get when you evaluate the sine, if you can mirror image reflect it across and it becomes the negative of the same thing, we call that in math being an odd function. So we say that the sine of an angle, the sine function is what we call an odd function, right? And what it means is the graph is symmetric. This means symmetric with respect to the origin. Notice what I mean by that. It means anything I take here, if I flip it and do it, like if there's a mirror right here across the origin, then I'm going to get I'm going to basically be able to fold this graph like this. Anything over here gets mirror image reflected over here. The 0 points get mirror image reflected over the origin as well, like this. Now, I'm going to draw the exact same situation for the cosine function. But let's just, before we even do that, let's just look at how the cosine function differs. The cosine function is different, whereas in the sine function, take a look at the pi over 2 situations. One's negative and one's positive, so it's a mirror image reflection about the origin right here. But let's look at a situation here for the cosine function. If I pick two of equal angles on the opposite side, let's say pi and negative pi, these are not mirror image reflections over the origin. These are literally giving me the same answer back. So whereas the sine function, when I take mirror image angles like that, I get the same number but opposite signs. For the cosine function, when I take a look at the same angle on both sides, I get literally the same answer back. This one is a mirror image reflection about the axis. I could literally fold this graph in half and it's the same thing. This is what you call being an even function. So an even function is when it's literally the function is a mirror image reflection about the y-axis. Any value, like this one over here, let's say at 2 pi, and then at negative 2 pi, they literally return exactly the same answer like this. So the negative and the positive angles, when I take the cosine, I get exactly the same answer. That's called being an even function. But for an odd function, it's not like that. I get the same number, it's just there's a sign difference. One is different in terms of the sign. So the next thing we're going to do is we're going to go through this whole thing again, and I'm going to prove to you why the cosine functions differently, and then from this we will define the idea of, in this case, the odd function, and then we'll define an even function, and then we will apply it to situations that are not sines and cosines, because these definitions of even and odd functions, they apply to any function. Any periodic function can be expressed as an even function or an odd function. So we have to learn those definitions. Okay, now what I'm going to do is write down the definition of what we call the even function that you would typically see in a textbook, and that would go something like this. For the cosine function, if you take a look at the negative version of the angle, you get exactly the same cosine as you get by the positive version of the same angle. Okay, this is called cosine of theta is what we call an even function. Right? What we're basically saying is the cosine of an angle is the same answer that you get if you take the negative version of the angle and take the cosine of it. So let's look at the graph first before we draw the unit circle. What we're saying is if I pick any positive angle and pick the corresponding negative same angle, what you get back is exactly the same cosine. That means it's a mirror image reflection about the y-axis, and that's exactly what you get here. So for an odd function, it's a mirror image reflection. It's like reflected and then reflected again. So it's a mirror image reflection. You get the negative of the value reflected catty corner like this. But for a even function like a cosine, it's just a mirror image reflection about the y-axis. All right, now let's take a look at the unit circle to figure out why this is the case. So I'll see if I can squeeze in a unit circle over here. So we have x, we have y. Let me draw some sort of unit circle superimposed on that. And now don't forget, we're talking about the cosine function now. So we're going to do the same sort of thing. What I'm going to do is I'm going to define some angle, which is the positive version of the angle. And I'm going to define another angle, exactly the same angle, but the negative version of that angle, which is the negative version of that angle, which goes below the axis. Exactly the same thing as we did before. The only real difference is that because we're talking about the cosine function, remember the cosine on the unit circle is the projection onto the x-axis. Sine is projection on the y, cosine is projected on the x. So how do I figure out what the cosine of this angle actually is? And actually my unit circle is lopsided, so I'm not going to get the exact same number here, unfortunately. If I had drawn a better, I guess I could try really quickly to draw a little bit better of a unit circle, then it would really come out something more like that. And then this angle would be up here touching like that. It's a little bit closer. Anyway, if you're taking the cosine of this angle, what is it going to be? It's going to be the projection down here onto the x-axis, which gives you a positive number. But what if I take the negative of that exact same angle? What is the cosine of this angle? Well, it's the projection, again, onto the x-axis. You get exactly the same number. So because the cosine, and they're both positive, right, by the way, so I'll just put a positive here and a positive right here. So if you take a positive angle and take its cosine, it projects here. If you take the exact same amount of an angle below the axis, we call it a negative angle, you get exactly the same projection, and they're both positive. They're both the same sign. If the angle is over here, it's going to project down to being a negative cosine. And then if you have the same angle down below, it's going to project to being a negative cosine. So no matter what the angle is, no matter if it's a positive angle or if it's an angle on the other side of the unit circle, if you take a positive angle and a negative angle and take the cosine of both of those, you get exactly the same answer because you're always projecting onto the x-axis, either over here or over here. And that's what this is trying to tell you. This is the textbook definition of what an even function is. If you take the cosine of an angle and you get the answer, and the cosine of the exact same angle but it being negative, you're going to get exactly the same answer. They're both positive. The answers are the same. And that's because of the way the projections work here. When you compare that to the sine function, because you're projecting onto the y-axis, if you take a positive and a negative angle, you get the same number, but they're opposite signs. So an odd function is whenever you take the sine of the negative angle and you get the exact same answer, but you just slap a negative sign onto it as you were taking the sine of the... It's so hard to explain in words. If you have a negative angle and a positive angle, you get the exact same answer. It's just one is the opposite sign of the other. That's what I'm trying to say here. Whereas in the cosine situation, we're doing the same exact thing, cosine of a negative angle, cosine of the positive angle, and we get exactly the same answer. Now, what this means physically when you graph it is that this graph is symmetric with respect to the y-axis. So if you had to memorize a definition, this is the definition I would want you to memorize, right? And this one right here, I would want you to memorize this definition. So for even functions, if I tell you, here's a periodic function that is even, immediately in your mind, I want you to think cosine function. It's a mirror image reflection about the y-axis. So all even functions are mirror image reflections about, or symmetric about the y-axis, just like this. It's just a mirror image reflection. Negative and positive same angles give you exactly the same values. Whereas an odd function, the graph is symmetrical about the origin. So what that means is negative and positive same angles, they're catty-corner to each other, mirror image reflection about the point, which is the origin. Same values, just opposite signs of each other. So I've motivated this discussion using sines and cosines because sines and cosines are by far the most important periodic functions that you will ever study in math. In fact, we're going to learn, or if you go on in math, you will learn that any periodic function, no matter what its shape is, if it's a triangle like this, if it's, a square pulse like this or whatever, you can write them as an infinite number of sines and cosines. And that is something you learn much later in math, but sines and cosines are very fundamental. They're like the building block ABCs of all other functions. Any other periodic function can be written in terms of sines and cosines, maybe an infinite number of them, or maybe a large number of them, but that is something that we learn about later when we talk about something called Fourier analysis. You get to that much, much, much later in more advanced university level classes. But I'm just telling you now so that you can, in your mind, it lodges in there and you say, oh yeah, sines and cosines really, really important. That's really all I want you to know, okay? But this idea of even and odd functions, it applies to more than sines and cosines. It applies to any periodic function. So in a textbook, you might see something like this. So in general, and now I'm opening this up so we're not talking about sines and cosines, we're talking about any, in general, any function. In general, okay, we say that the function f of x is odd. F of x is odd function if the following is true. And what we say is the definition of an odd function is that the function evaluated at negative x is the same thing as the negative of the function evaluated at x. And we also say that the function is symmetric about origin. That's what this means. These are two different ways of saying the same thing. Now this definition here, I'm just using generic f of x, but it's exactly the same thing that we already wrote down for the sine. The sine of the negative angle is the same thing as the sine of the positive angle, but with a negative sign slapped on front. If you put a negative, this is like taking two equivalent values on either side of the origin here. You have a positive x value and the negative. This is like putting a negative 3 and positive, or this is like putting positive 3 and negative 3 into a function. You get exactly the same answers, except one is negative version of that. And that means that it's symmetric, catty-corner symmetric about the origin, which is exactly the way the sine works. But any function that we call odd behaves this way. All right? And then similarly, we can write down the general definition of what an even function is. F of x is even if, whoops, I can write down if correctly, if, what do you think we're going to write? We take and evaluate the function at negative x, and we get exactly the same answer as if we evaluated at positive x. So we take two values, one like a positive 6 on the right and one negative 6 on the left, and we put them both into f of x, and we get exactly the same answer back. So we say this is symmetric about the y-axis. And that's exactly the way the cosine works. Pick any, any value here, positive angle and negative, or positive value of x, negative value of x, you put it in there and you get exactly the same answer back. So that is what I want you to remember. These are the mathematical definitions of the even function. You put a positive value of x in, negative equivalent value of x in, and you get exactly the same answer. We call that even. And if you get the same thing back, but one's negative version of the other, we call that odd. I've also drawn the unit circle to show you how it happens specifically for sines and cosines, because that's by far the most important periodic functions, but the idea of even and odd functions apply to any function that we have. All right, now what we need to talk about, I think we've actually got through the most important parts of the lesson. The next thing I want to talk to you about is something shouldn't come as a shock to you, but let's just talk through it, okay? What we said is that the sine function is a periodic function. It has a period of 2 pi. So that means that as we go 2 pi distance along the x-axis, then the thing begins to repeat. If we were to go another 2 pi, meaning we end up at 4 pi, then it would begin to repeat again. If we go another 2 pi, meaning that we go to 6 pi, it begins to repeat again. Why is that the case? Because if we start on the unit circle, we go 2 pi, then the angle is really the same as the one we started. And then if we go another 2 pi for a total of 4 pi, we again are where we started. If we go another 2 pi to 6 pi, and then 8 pi, and then 10 pi, and 12 pi, and so on, every 2 pi we go around, then we get back to the same place on the unit circle. So this graph is going to end up back to the exact same starting point. That's what a period of 2 pi actually means. So what we can say mathematically, okay, what we can say mathematically is that, what we've already said mathematically, is that the sine and the cosine function have exactly the same shape, but they're shifted relative to each other. They both have the same shape, they're shifted relative to each other, they both have a period of 2 pi. So mathematically, when we say something has a period of 2 pi, what we can say is that the sine function, if you put into the sine function whatever some angle is, and then add 2 pi to it, what you get back is exactly the same thing as the sine of the angle that you started with. And we can write the same thing for the cosine. The cosine of theta, and then if we add 2 pi to it, we're going to get back the same thing that we get if we just take the cosine of the angle here. So these are things that you see in textbooks, but if you don't know what a periodic function is and it's not like something that you're very comfortable with, then it's easy to overlook these and ignore them and say, I don't care. I'm scared of it. Don't be scared of it. What this is telling you is that if I start anywhere, let's say I start right here. Here's an input of 0, and I take the sine of it and I get 0. Now, if I add 2 pi to it, then I'm going to end up here. Let's say I now take the sine of 2 pi. Again, I get 0 back. So every time I add 2 pi to the angle that I'm taking the sine of, I should get exactly the same answer back. Why? Because no matter where, let's say I start at this angle. I'm going to take the sine of it, I'm going to get some value back. But if I add 2 pi to it, I'm going to be in the same place. If I take the sine of it, I get the same thing. If I add 2 more pi to it, maybe 2 more pi to it, and 2 more pi to it, I'm in the same place. I keep taking the sine, I get exactly the same thing. So for any periodic function, in this case I'm just talking about sines, if I take an angle and I take its sine and I get an answer, and then if I take the same angle and then just add 2 pi to it and take the sine again, then I get the same exact thing. That's why they're equal to each other, right? If I do the same thing with cosine, it's exactly the same thing. If I take the cosine of, pi over 4 radians, right? That's an angle, pi over 4 radians. I get an answer. I'm going to get square root of 2 over 2 back here. Then if I take pi over 4 radians and add 2 pi to it and then take the cosine again, I'm going to get exactly the same cosine back, square root of 2 over 2. And that's because cosine is a periodic function. So any angle I take, let's say I start right here at pi. So I have, this is what the cosine of it is, right? If I add 2 pi to it, I'm going to end up here. This is 1 pi, and I add another pi. Now I've added 2 pi to the angle. I take the cosine, I get exactly the same thing. For sine and cosine, if you add 2 pi to it, to the angle, you're going to end up with exactly the same value of the function back. It's the same thing here. Because if we're taking the cosine here, if I start here and add 2 pi, then I'm going to get exactly the same cosine no matter how many times I go around adding 2 pi to it. And that is why, by the way, why is 2 pi the magic thing? Because sine and cosine have a period of 2 pi. So when you have a periodic function and you know what the period is, if you add 2 pi to the input of the function, or whatever the period is, then you're going to get the same value of the function back because that's what a periodic function is. It always repeats itself, so if you advance one period in the future again and again and again, you're always going to get the same exact answer back. All right? So this is how it applies to sines and cosines. But again, we can say something like this in general. In general, we can write down something that you see in your book, and a lot of students just overlook it and you don't really care. If you have a function and you have an input value of x and you add to it some period, which you know the period of the function, you're going to get exactly the same value back as if you just stuck x in there. And I'll say where p is the period. Right? So if I have some function, some periodic function, could be a sine, could be a cosine, could be some other periodic function that I just make up. It could be a sawtooth wave with some period like I showed you in the beginning of the lesson. If I evaluate the function at some value of x and I get an answer, and then I evaluate the function again at the same value of x, except I add to it one period, which means I'm going down the line by that period, and then I evaluate the function again, I'm going to get exactly the same value of the function back. In fact, we can go back and look at our original sawtooth. This is a periodic function we did for problem number 1. If I start here at -2 and I evaluate the function, I get the value of 1 back. We said the period of this is 2, so we go 1, 2. We advance one period, evaluate, we start here, advance one period into the future, and do the same thing. We get exactly the same thing back. If we go again one more period, so that's a period of 2, we get exactly the same value back. So this is a generic statement that applies to any periodic function, which is a function f of x, where I advance one period into the future and evaluate the function again, I get exactly the same value back. All right, now we're basically done. I've done, I think, the essentials of what I really want to get back into this lesson. What I want to do for the last two is I want to draw 2 graphs on the board, and we're going to answer the question, are they an example of an even function or an odd function? And they're not going to be sines and cosines. So let me just try to sketch this guy. So problem A, I guess I'll say. Let's go ahead and draw this guy. So it's not going to be perfect, all right? It's not going to be perfect. So here's x and here's y. Let's draw a graph here. So this is 1. And I'll say down here, this is -1. And what I'll do is I'll go down here, and then I'll go down here, 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 you know, like this, something like this. And then I'm going to continue this way, whereas I've, you know, kind of go down here, and then it's like here, 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 something like this. Now, what are the numbers on the x-axis doesn't really matter, but I could just say, you know, this is 1, this is 2, this is 3, this is 0, so this is -1, this is -2, this is -3, something like this. Is this an even or an odd function? All right, what you're looking for is basically if you take two equivalent, if you march in both directions, what do you get? So if we go over here and we go to +1 and -1, or let's not pick because that's where the vertical lines are. Let's go to +1/2 and -1/2 right here. Well, at +1/2, the function evaluates to be +1, and at -1/2, it evaluates to be -1. So these are the same exact value, but opposite signs of each other. If you go over here to 2.5 and negative, this is -1, -2, -2.5 down here, again, you get a +1 and a -1. And so no matter what angle we pick, we get a evaluate on one side, and on the other side, we get exactly the same number, but opposite signs. Another way of saying that is this is a mirror image reflection through the origin. This gets reflected down to this gets reflected down to this gets reflected over here to this. So this is what we call an odd function. This is an odd function. And the example of that is exactly the same as this, which of course the sine function is a much more smooth function, but you get the idea. This is a mirror image through the origin. This is a mirror image through the origin. If we take same angles, we get basically opposite signs on the numbers, but the actual absolute values are the same. So let me draw our last problem. We'll say this is B, and I'll draw, again, it's not going to be great, but I'll draw something similar like this. So this is X, this is Y, and this is, you know, 1, and this is down here -1. How do I want to draw this? So what I want to say is, okay, I'm going to go here like this. So we're going to go down here, right, like this, something like this. These are supposed to be equal widths, which I'm not drawing exactly right. Something like this. But what are the numbers? They don't really matter. I mean, this could be, you know, this could be 1, this could be 2, this could be 3, -1, -2, -3, same thing. But you see the difference? This is a mirror image reflection about the axis. Here, if you're at like +1/2 and -1/2, you get exactly the same answer coming out of the function. If you're over here and you're over here, this is the same distance away, you get like a +1, +1. If you're down here, whatever this angle here, whatever this input is for X and the input is for X, positive and negative versions, you both get -1 out. When you march the same distance on both sides, you get exactly the same value of the function back, so we call this an even function. And notice the way it's reflected. It's a mirror image reflection, not about the origin, but about the y-axis. So we've done a tremendous amount of material in this lesson. I had to kind of put it all together because if you talk about what is a periodic function and then you split up even and odd functions, then you lose a little bit of the continuity of what you're doing. But basically, periodic functions are important in nature. A lot of you know, random noise and things like that are not periodic. There's nothing that's repeating going on here. But you have these nice periodic functions that show up in nature over and over again. When you have a periodic function, you can define a period p, which is the distance over which the thing begins to repeat. And that's going to be a number, okay? And then you could say, well, let me give you a fragment and say this is a snippet, and I'm going to say I want you to redraw the thing as if this were a snippet and the function had a period of 2. Then you would just repeat itself, and you can see the distance from here to here is 2. The distance from here to here is 2 units, so this is a periodic function. Remember, periodic functions go on and on forever. The most famous periodic functions, the ones that are really important, are the sine and the cosine functions. In my personal opinion, some of the most important functions in all of math and all of science. So this is the sine function. We're going to learn how to graph it a lot more later, but you can see it's this wave shape, and the period of it, where it starts to repeat, is 2 pi. The cosine is exactly the same thing, but it's a shifted version. The cosine starts at the crest, whereas the sine starts at the 0 point here, but you can see it begins to repeat itself again after 2 pi there. So sine and cosine, when they're not changed or altered, they have the same period, they have the same shape. They're just shifted relative to one another. Why are they so similar? The reason they're so similar is because sine and cosine come from the unit circle. The sine is the values that you get when you pick an angle and you project it onto the y-axis. The cosine are the values that you get when you pick an angle and you project it onto the x-axis. So as the angle spins around here, eventually when you get back to 2 pi, no matter where you start from, you end up at exactly the same place that you started. So the sine and the cosine, when you go around 2 pi, will be exactly the same values. That's why these have periods of 2 pi. All right? And then we talked about the idea of even and odd. We said that basically an even function is a function where when you have the same angle, positive and negative values of the same angle, you get exactly the same value back, which means it's a mirror image reflection about the y-axis. If it's a same value but catty corner, so one's positive and one's negative, reflected about the origin, we call that an odd function. The best example of an odd function is a sine function. Right? And the way you write it, see it's a graph symmetric about the origin. The way you write it is you say, if you have the positive version of the angle and the same angle but the negative version of it, you get the same sign back, except one is a negative version of the other. That means it's symmetric about the origin. But for the cosine case, right? For the cosine case, we call it an even function because if you take a positive and a negative same angle, but one's positive, one's negative, you get this exact same value back, which means it's symmetric about the y-axis. We call it an even function. And the reason why they work out that way is because if you have one angle positive, one angle negative, they both project to the same exact place on the unit circle for the cosine, whereas for the sine, they project to same distance, but one being positive and negative onto the y-axis. That's why that is the difference between sine and cosine. And we can generalize this point to say, in general, any function is what we call odd if it behaves that way. If you take a positive and negative input value, the same number, but one's positive, one's negative, and you get opposite signs back, we call it odd. If you do the exact same thing, but you get the same value back from the function, we call it even. And then we rounded out the entire lesson by saying that any periodic function, and specifying the case of sine and cosine, if you take the sine of an angle and record, or the cosine of an angle and record that value, if you take the same angle and advance it by one period, in this case the period's 2 pi, take the sine again, you're going to get the same thing because the thing repeats. Same thing for the cosine. So you generalize that to any function. If you have a function evaluated at x, record the value. And if you evaluate the exact same function again, but where you take x and you advance it by one period in the future and evaluate the function again, you're getting exactly the same value back because it's a periodic function where p is the period. Then we talked about even and odd applied to something other than a sine and a cosine. So a lot of stuff to talk about here, but we're building the foundation. What I'd like you to do is go through this again, make sure you understand it, maybe watch it twice. Follow me on to the next lesson. We'll draw more pictures of periodic functions. Then we'll graph sine and cosine in a lot more detail. Then we'll start shifting sine and cosine around. How can we squish it this way, squish it this way? How can we change the way it looks so that they don't all look the same? And then we'll be practicing graphing all of these trigonometric functions, which are extremely useful as we go on into more advanced science, math, and engineering. So watch this, maybe watch it twice. Follow me on to the next lesson. We'll continue to work on periodic functions.